Thanks. Okay, so good afternoon, everyone. Today I'll be starting uh, discussion about quantum algorithms which have been used already for quantum chemistry calculations. Today I will talk about quantum phase estimation and HHL algorithm. And tomorrow morning, Professor Guidoni will be talking about variational quantum eigensolver. So the two algorithms that I'm going to talk about today, they are basically fault tolerant algorithms. So they cannot be successfully implemented in the current near intermediate scale era of quantum computers. So they will always they have theoretical speed up over the classical counterparts. So quantum phase estimation is basically equivalent to diagonalizing a Hamiltonian classically. And HHL is a quantum linear solver, so it tries to solve linear equations using a quadratic speed up than the classical algorithms. So let me begin with the quantum phase estimation. How to uh, no, the slide of this. Just in your code. Okay. 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 So quantum phase estimation is algorithm which finds the eigenvalue of any unitary operator. So it finds the eigenstate and the corresponding eigenvalue of any unitary operator that can be given. So it can be very useful for molecular systems to find the energy of the Hamiltonian as well as the corresponding wave function associated with the molecular Hamiltonian. So as I was saying in the previous lecture of about quantum chemistries, uh, I showed you the configuration interaction method, which basically is a Hamiltonian which has to be diagonalized to get the ground state energy and the wave function. So QPE can be thought of as equivalent to solving a CIE Hamiltonian, and it also has use in other quantum algorithms such as Shor's algorithm, which is very useful for quantum cryptography for factorizing integers into prime numbers. And it is also a part of HHL algorithm, which I'll be talking about later, which has its own application in quantum chemistry, and it's a very recent application that has been done. So as I mentioned, both of the algorithms are very high depth. So it has a lot of gates. It requires a lot of gates to do its job. So it's a fault tolerant error algorithm. So we are waiting for maybe a lot of error correction and error correcting qubits to come. So logical qubits to be high in number so that we can successfully implement them on an actual quantum computer. So as I was saying, QP tries to find the eigenvalue of any unitary operator. So say uh, we have a unitary operator. So this is our unitary operator whose uh, eigenstate is psi, and the eigenvalue is lambda, and it can be equated to. So it can be equated to a form such as exponential of 2 pi I. Now, can anyone tell me why the eigenvalue can always be expressed as exponential of a 2 pi I theta kind of thing? Sorry. Yes. So which property of the unitary operator can guarantee that it will be of this form? Anyone? So why will the eigenvalue of a unitary operator can be written as an exponential of I theta kind of thing? So cos theta plus I sin theta. Yeah. Uh, yeah, I mean this eigenvalue can be complex, of course, but I mean any real number cannot be written as exponential I theta. It has to have some property. So what is the property? So let me just if I just write it, you will if I just write it once, you will understand. It's very easy. So the property of unitary operator. So the property of a unitary operator is that uh, acts on a wave function. Sorry. But can it be seen in the yeah, I mean whenever I press this kind of gets off. Wait, hold it. Yeah, I mean whenever you're trying to write it, this one is getting pressed and it's going to select. So where do I hold it? Like okay, okay, so I hold it like here. But I'm not getting the dip.
Can still feel
Now, oh, this is maybe better. The bottom.
Yeah, I need to press the button to see it.
Oh,
Okay.
Yeah, I think so. So property of a unitary operator is like we square it. So u psi square. Since unitary operator is the square of itself, so u it can be written that u square equal to u. So u psi square equal to lambda square psi square. Anyway, I mean we can show that lambda square equal to 1. And lambda has to be within 0 to 1. So any real number within 0 to 1 can always be expressed as in the Euler formula. So lambda can always be expressed by exponential of I2. And the choice of theta to be like 2 pi omega is just algorithmic for our algorithmic simplicity, so that theta can be expressed as a fraction of complete rotation, because 2 pi means 360 degree, and so that omega remains like it can be written as a fractional value, so that it remains within 0 to 1. And the other thing is, I guess you already know that any number within 0 to 1 can always be expressed in terms of, I mean, it can be transformed to a binary form in this form, like 0 point, some binary sequence of number. So everybody is like, everybody knows this part, like decimal to binary conversion. I mean, any decimal number can be converted to a binary representation. Okay. So it is very easy. You just have to multiply the number by 2 successively and take the part before the decimal and put it in the binary form. So now coming to the, sorry, have to erase this every time. Okay. So now that we have understood the properties of a unitary operator and on its eigenstate, which is psi, let's look at another concept needed for quantum phase estimation, which is a control unitary. So you've already learned about controlled logic gates, I guess, in the introduction to quantum computing. So what basically a control gate does is if the qubit on which it is controlled has the value 1, then it lets the logic gate act on on the target qubit. So here, for example, if it is 1, then it will the well, yeah, so it's already written. So it will let the operator U act on psi. So what this essentially means here is in our case, the equation we already have defined the action of U on the eigenstate psi, which is exponential of 2 pi I omega. So when the control qubit is 1, the action of U on psi occurs, and we get like, so in this case, so it happens like 1 acts on psi from here. And since this is a constant value, so we can always move it back to the first qubit, that is the control qubit. So this is what is called a phase kickback. So the omega phase no longer stays in the second qubit. So the phase is the eigenvalue of the state of the unitary operator U moves to the eigenvalue omega is now inside the control qubit. So this is what is known as phase kickback. So the phase is kicked up to the control qubit from the target qubit. And this is an essential part of the quantum phase estimation algorithm. Okay, so this is up to this is okay. So the next concept that is needed before we finally proceed to the quantum phase estimation, the algorithm, the circuit is quantum Fourier transformation. So what is quantum Fourier transformation? It's have you heard of Fourier transformation in classical sense? So it's just a basis transformation between two orthogonal bases. So here, what is done usually in quantum Fourier transform, we just go from the computational basis, that is the basis of 0, 1, or for a higher qubit number 0, 0, 0, 1, 1, 0, 1, 1. From there we go to some other basis which is also orthogonal, but it's like a linear combination of the computational basis. So it's basically a change of basis for all the quantum states from a computational basis to some other orthonormal basis. And the general structure of Fourier transform. So this is the relation between the variables in one basis to another. So y is in the basis of k, while x is in the basis of j. And we are basically transforming it from, so x is defined as sum over of j x j j in the basis of, this is the basis in which x is defined. So these are the two different orthogonal bases in which the Fourier transform helps it to transform, and this factor is essential. This is the Fourier transformation factor, which basically helps to change the basis between one another. So the equations in both classical and quantum Fourier transform are very similar. What is different is, so the difference you can also see here that in classical Fourier transform, it was just a number. We were just changing a variable dependent and here it's a superposition of states. So it's a vector now from just a variable dependent on parameters. So so this is the general structure of any functional of any Fourier transform function. It's 1 over root n and exponential of 2 pi I j k. And as you know that any quantum gate can be written as a unitary matrix. So the quantum Fourier transform can also be written as a unitary matrix. And the trick to kind of convert uh, how to construct a matrix corresponding to a quantum gate is you just, I mean, say I'm defining this 2 pi I by n. So this 2 pi I by n as omega. So now it becomes like 1 by root n omega into jk. So what is jk? Jk's are the basis of the basis which are transforming within each other. So the dimension of this of the unitary matrix of quantum Fourier transform will be j by k. So this is the 0, 0 element. This is the 0, 1 up to n minus 1. And hence here also it's 1, 0, 2, 0, and so forth. So on. N minus 1, 0. So the way you can, I mean, you can do it yourself. You can construct the values of the matrices. You just, since it's now e to the power omega into jk. So j is when j is 0. So the first element is j equal to 0, k equal to 0. So it's exponential of 0. So it's 1. The first element is 1. Second, so basically the first row j is always 0. So any of the first row element is exponential of 0. So each element is 1. In the next one, if you see, it's also starts. So the first column and the first row will always be 1. The next one is the 1, 1 element. So it becomes exponential. So it becomes exponential of 2 pi 2 pi I by n into 1 into 1. So it's basically equal to omega. So that's why it's omega. Similarly, the next one is 1, 2 elements. So it's omega squared and so on and so forth. So you can, in any quantum gate, you can kind of derive its unitary matrix by yourself by just following the basis in which the quantum gate is acting on. So it's is this the creation of this matrix clear? Okay. So for example, I mean, now you can construct the QFT matrix for, say, we are doing it for n when n equal to 4. So 4 means 2 square. So the dimension of this will be a 4 by 4 matrix. And by using the same formula, you can, so when omega, say, I'm defining the omega, the phase, the eigenphase as I, then it will be just the first column is 1, 1, 1. Next one is omega squared is 1. Omega squared I squared is -1, and so on and so forth. So it's a very simple structure. So now coming to the circuit form of the quantum Fourier transform. Assuming that we have a binary, we already have a binary expression of a decimal number, and it's of the form. So n1, n2, n3 binary form means is like basically like we wrote point. So 0.8, say 0.71, some 5 can be written as 0.111 or something like that. So n1 it will be 1, n2 will be initialized to, and n3 will be 1. So this is the meaning of this n1, n2, and n3 in the binary form. So what the quantum Fourier transform circuit looks like, we have a Hadamard gate on the first qubit, a control rotation on the first qubit for which is controlled upon the second one, another control rotation on the last one, a Hadamard again on the second qubit, another. So it's kind of a cyclical structure. And control rotation gate, basically it's like a phase gate which is controlled over another qubit. So this is the general structure of a rotation gate. And control rotation is just you have a unit operator here, and so now let's try to see that why does this circuit exactly do what we showed before analytically. So does it really change the basis from one to another? Let's just check that. So to look at the action of gates in a circuit, what we do, we divide it into, we evaluate the state at each part. So we divide it at, so this is step 1, 2, 3, 4, 5, and 6. So we have to trace this evolution of the direct product of these 3 qubits, that is the states n1, n2, n3, along this whole path. So at the application of each gate, we check how the state looks like, and then finally at the sixth step, we have our target state. So let's quickly go through how it looks like. So for this first step, so the first step is Hadamard acting on the first qubit. So when Hadamard acts, this is the general form of the action of Hadamard on a qubit. So since we don't know, since we're generalizing N1, we don't know whether it is 0 or 1. This is the general format of Hadamard gate. So e to the power 2 pi I. So when N1 is, when it's initialized to 0, so it becomes 0, 2 pi I 0 by 2. So it becomes 0 plus 1 by root 2. And when N1 is 1, 0 minus 1 by root 2. So this is the general structure of a Hadamard output. And the rest of the qubits remain intact because we have no gate acting on them. The next step, we are having control rotation on the first qubit, which is controlled over the second one. So the control is on the second one. And as we had seen, what happens when a control rotation acts is we already had 2 pi I N1 by 2 by the action of Hadamard. And now due to the control rotation, if you remember the form of the control rotation, it's 2 pi I by 2 to the power m. So since it's the second qubit, which is on the control, we have a 2 squared form factor here. So the control is over N2, so N2 by 2 square picks up on the 2, it is rotated by this phase, and a phase is added on this one. And when the second rotation acts, another phase is added. So these two are the phases by which the state gets shifted by whenever the rotation is acting. So it's shifting only on the first qubit because we have a control gate here. It's not doing anything on the 0 because of the controlled rotation structure. So till now, we have only been doing the operations on the first qubit. This is still intact. And if you remember the full circuit, there is nothing after this. So there is no more evolution on the first qubit. So we can write this as, so this is the final final equivalent of, so omega 3 is the equivalent of N3 in the Fourier basis. So this is the transformation of one of the qubits is already done. So N3 has already been pushed up. So the phase kickback has already here acted upon. So now the same procedure will happen on the second one, but since there's just one qubit underneath it, there will be only one rotation gate. So then we have another Hadamard. So the same thing happens here. We have added a N2 by 2 here. control rotation, which is controlled over the last qubit. So we have an n3 by 2 square. And this is the transformed form from the computational basis to the Fourier basis. Similarly, so for the last one, since this is only a 3 qubit example, there is no other qubit to control the rotation. We don't have to do anything on the last qubit. So there's only a Hadamard gate here. So one thing that is interesting to understand here is that if you remember the general structure of a Fourier transform, the QFT matrix form was 1 1 omega square and so on and so forth. So for n equal to 2, for a 2 qubit, for just 1 qubit case, that is it reduces to 1 1 minus 1. So basically this is equivalent to a Hadamard gate. So Hadamard gate is equivalent to a 2 qubit quantum Fourier transform. So that is why when we have the last qubit, this is equivalent to a 2 qubit Fourier transform, and we get, so this is our last transformation to the Fourier basis. So as you can see that the way this circuit is has been developed is when we the equivalent, the Fourier equivalent of n3 of the third qubit moves up to the first one. So when we measure n1, we actually get the order is reversed. We had n1, n2, n3. N1, N2, N3. But what we get back is in the reverse order. Epsilon 3, epsilon 2, epsilon 1. So what we need to do so that we can understand that when we are measuring it, so that it comes in the same order is we use something called a swap gate. So we swap all the qubits, the location of the qubits. And so what this looks like is basically so this is a generalized version of the QFT gate, not just for a 3 qubit. So we have Hadamard on each qubit, then control rotations controlled successively on each of the qubits underneath, and the last qubit just has a Hadamard. And at the end, since the order of the Fourier transform basis is reversed, this is called a swap gate. So this is a swap gate, which basically swaps both the qubit on which it acts. So a swap on 0 0 will give 1 1, 0 1 will be 1 0, and so on and so forth. So a swap gate essentially swaps the order of the qubit states. So since we had it in a reverse order, epsilon 3, epsilon 2, epsilon 1, it will, after the application of swap, it will reverse to epsilon 1, epsilon 2, epsilon 3. So now we have successfully kind of changed from the computational basis by which the binary was defined to a new basis which is defined by these values. Now, we have introduced two concepts here that we will use in QP. One is the kickback phase, which is done by using ancilla qubit. By ancilla, I mean an extra qubit that we need. And we act it on a side. This is the ancilla. If we apply a unitary on it, then the phase, the eigenvalue of the unitary eigenvalue moves to the ancilla qubit. And the other concept that we introduced is the quantum Fourier transformation, which is just a basis change from a computational basis to another orthogonal basis to the computation one. So now these two concepts will be a part of the QP algorithm. Okay, so just recapping what we want to do again, because after introducing QP, I introduced two more kind of circuits. So we just want to find out the eigenvalue of a unitary operator. The unitary operator is defined as a number between 0 to 1, so it can be represented in binary format. We want to obtain a good estimate of the eigenvalue. We know nothing about the eigenstate. We only know the unitary. So what is the only assumption for a QP algorithm is that operator U can be efficiently implemented as a quantum gate. So assuming that U can be implemented as a quantum gate, we move on to the steps in a QP algorithm. So we need some ancilla qubit whose power n is, it defines the precision of the eigenvalue, precision of omega. So the more precise we want the eigenvalue to be from the quantum phase estimation, we make the n value of n higher. Next is the eigenstate of the operator that we have to initialize. So this is the eigenstate of operator U, whose eigenvalues we want to find. We apply Hadamard to each of the control register. By control, I mean the ancillary registers. Then we apply controlled unitary operations. So this is what is the phase kickback. So this controlled U to the power 2k will transfer the eigenphase omega onto the control register. And finally, when we have all the eigen phases of corresponding to each of the qubits in the psi, we finally have to now, since it's in a binary format, we have to take it back to the computational basis. So this is like a reverse of a quantum Fourier transform. So that's why we're calling it the QFT inverse. So what QFT did was transform state from a computational basis to a Fourier basis, but now we already have it in the Fourier basis after applying controlled unitaries. And so we have to now take it back to the computational basis because we want to measure it and find the eigenvalue. And then finally we measure the control register and we have the eigen value of the unitary. So moving on to the circuit structure. So as I said already in the steps of the algorithm, the first, so these are the extra qubits that we need for the algorithm to work. Extra or ancilla qubits. This is the eigenstate corresponding to the unitary operator. So we don't know exactly the eigenstate because it's we don't know the eigenvalue of the unitary. So usually what is done in QP, we start with a guess psi, which is closest to, if it is a physical system or a chemical system that we are solving, we try to take it as close as possible to the problem Hamiltonian. For example, when we try to solve for a molecular Hamiltonian, we initialize the psi to be the Hartree-Fock wave function. So that gets us, that is a good approximation to the exact wave function. So we have the ancilla qubits. We use the control unitary rotation. Each control unitary rotation then kicks back or transfers its eigen phases to. So this one kicks back such eigenphase here because it is controlled over this qubit. This one is controlled here, so the eigenvalue, so we can call it omega 1, omega 2, and so on and so forth. So this is how the individual eigenphases are transferred in each of the control registers. Next, this basically brings back the omegas from the Hadamard basis or the Fourier basis to computational basis. Then when we read out, we get the eigenvalues as a in the computational basis. And so say we are getting here 1, 0, 1, 0, 1, then we can easily transfer it back to the decimal, and the decimal value would be, say, it's 0.85 or something. This is our required eigenvalue. So it's a very simple procedure, but it has a lot of parts that it is divided into. So the first part sends individual binaries in the Hadamard basis to the control qubits. We have a QFT inverse which brings it from the Hadamard to the computational basis. We measure it. We get at each of the control qubits the values. Then we convert it from binary to decimal directly. And this decimal value is our energy or eigenvalue, whatever the unit is. So basically, this is what I just explained, shown mathematically. So when the Hadamard acts on the ancilla, it goes to a mixed basis. There is a Hadamard basis, followed by the controlled unitary, which acts on each of the qubits. So this is basically the phase kickbacks, all of the phase kickback together, eigenphase. Feedback. It accumulates and we get this form. So this basically uses the just the properties of exponential and exponents. When we multiply exponents, it just adds up and we get a sum over k equal to 0, and we can write it like this. And this is basically the Hadamard basis, the Fourier or Hadamard basis. So now we have to transform it from the basis of the Fourier to the computational basis so that we can measure it and get the we can measure it classically and get the value in the decimal case. Okay, so we have to convert from K to the basis of X by Fourier transform, but in reverse. So finally, what we get from QP is this. This is our final phase, and after measuring the control register, we get our omega as what we read out divided by. So basically, this is just converting the binary to a decimal form. So when we are going from decimal to binary, we have to multiply the decimal number by 2 till it goes to 0 point something. So it's the same thing when we go from binary to decimal, divided by 2, divided by 2 n times so that we can reach the decimal value. So that's how we finally get our eigenphase. So just a quick so this whole process, what does it mean for when we try to solve a quantum chemistry problem? So for a molecular Hamiltonian, we just have to the unitary operator U is the Hamiltonian. So the Hamiltonian can always be written as a unitary operator, such as exponential minus IHT. So for a quantum chemistry problem, this becomes a unitary. This is the Hamiltonian operator. Since Hamiltonian is Hermitian, an exponential of a Hermitian operator is always a unitary operator. So we get the unitary as such as this. We use the QP circuit. So here the U will be exponential of minus IHT. We find the eigenphase in the Hadamard basis. We transform it back to the computation basis we did out, and we get our desired eigenvalue. So since we defined our unitary as exponential, I mean, it is defined for molecular Hamiltonian as e to the minus IHT. Its action, so U psi, its action will be like e to the power I et. If we call E as the is the eigenvalue of the energy, the ground state energy of the molecule. So when we get omega, basically E can be found out by omega divided by IT. So we find omega from the measurement of the ancilla qubits, and then we get energy directly from the circuit. So the beauty of this thing corresponding, I mean, compared to the classical calculation of the molecular Hamiltonian. So there we have to diagonalize it. So as you know, diagonalizing Hamiltonian or diagonalizing a matrix is always a very costly procedure for a large basis. It scales as n to the power 3. But here with quantum phase estimation, with quantum phase estimation, we don't have to diagonalize the matrix. We get the eigenvalues directly from the circuit. But the only problem is, which I mentioned at the beginning, is as you can, I mean, you can well see that the circuit is huge. So if you want a good precision, then also the circuit will increase in the length of the number of control unitaries which is being applied. If the basis increases or if the molecule size increases, the value of m will increase. So m depends on the system size. So if we go to bigger and bigger molecules, the m will increase. And this depends on the precision that we want. So to get a precise energy for a large system, this circuit is too big, and if we even try to solve it on the current quantum computer architecture, it's like it will be so noisy you will maybe get nothing out of it. But when we get a good, hopefully in the next 10 years or 5 years, we can get a good error correcting qubits, and we can use this to get a speed up over the classical way of solving for Hamiltonians. So now that the QP is done, let's move on to the other algorithm that I wanted to show. This is an algorithm which had not been used in quantum chemistry till about 2 years ago. This was mainly used to solve optimization problems, quantum finance problems, because those equations are mostly linear equations. And so what HHL exactly does is it solves any equation of the form Ax equal to B. And it does so by inverting the matrix A. And it inverts it and applies it on the state B, and we get our solution. So this is our solution X. So the only conditions that it needs, the algorithm, is the matrix should be Hermitian, because we have to exponentiate it at some point. And as I said, exponentiation of Hermitian matrix is always a unitary operator. And unitary operators can be written directly as quantum gates. So that's why this condition is there. But there, even if the matrix A is not Hermitian, there are ways to get around the this kind of rigid condition. And normalization of the vector B is also, I mean, it's not a very rigid condition. You can normalize any vector anyway. You'll just have a norm factor on the vector every time. So as I was saying, even if A matrix is not Hermitian, you can make it Hermitian by force, by increasing the dimension of the matrix. So if A is not a non-Hermitian matrix, you can always make it Hermitian by you can make it Hermitian by embedding it in a larger matrix. So if the dimension of A was n by n, the dimension of the Hermitian matrix will be like 2n cross 2n. So the dimension will just double. And similarly, you have to transform the other variables, that is the vector x and the vector b, so that they can be used in tandem with the new matrix. And the modified equation becomes now A tilde X tilde equal to B tilde. So now you just apply HHL here and you solve for X tilde. Okay, so the steps of the HHL algorithm, I will first go through the steps and then afterwards I will explain why the steps are like this. So we first load, we need three registers for the HHL algorithm. The first register is where we load the vector B of AX equal to B. So if you remember, the equation was AX equal to B. A is the matrix, X and B are vectors. So first we load B into a register. We need another register which will act as a control, which will be controlled on the register of B. We will also need an additional control register, which is called the NA. This will help us to invert the eigenvalues of matrix A. And finally, we have to do an inversion of QPEs. I will just explain why we need both QPE and QPE inverse to do the matrix inversion. So let's quickly move on to the circuit. So this is the general structure of a HHL circuit. We have this is our vector B. This is known. We already know this. So in the equation AX equal to B, we know A and B. These two are known already. We just need X. So we can load B, we transform B into the computational basis, we write it to the computational basis and load it here. We apply a QPE, and if you remember what QPE does is it finds the eigenvalue of a unitary. So here the unitary will be the unitary which we are solving here is exponential of IAT, which is why we had said that A should be Hermitian, so that it can be written as a unitary very efficiently. So what it does, it finds the eigenvalues of A. So in these registers, we have the eigenvalues of A. The next step, what it does, this is a control rotation. Well, this is the control. And this is the target. So the target contains the eigenvalues of the matrix A. What control rotation essentially does, it inverts the eigenvalues. So say the eigenvalue of A, if I call it lambda, what control rotation does it, after rotation, it just brings it to 1 by lambda. So this is after control rotation. And as exponential variety is a unitary operator, we know that the eigenvalues of a unitary operator and the eigenvalues of the inverse of the unitary operator. So if you, so this should not be A, sorry, this should be U. So using the property of unitary operators, we can say that if the eigenvalues of U is lambda, then the eigenvalues of U inverse will be lambda inverse, equal to 1 by lambda. So what we are trying to do essentially in HHL, so that we can invert the matrix A, we load the matrix A as a unitary, find its eigenvalues, we invert the eigenvalue, then we again go back from using QP inverse. So from 1 by lambda, we go back and here we have A inverse. So after the second QP in reverse, from 1 by lambda, we get A inverse. And so this is A inverse acting on B. So since it is on the B register, A inverse acting on B is our required X. Now we can do a variety of things with this X, because I mean, just knowing X is not enough. We have to get some observable from it so we can compare it with something classical. So that's why this fx function is there. I will explain, I'll give an example of how fx or a function can be used to get something meaningful or physical in chemistry. So this is the basic idea of HHL. The steps, steps are really simple. We just exponentiate the Hermitian matrix to get a unitary. We get its eigenvalues, we invert the eigenvalues, we again do an inverse QP, and we get the A inverse matrix and apply it on the state B. So the same thing, it's just shown in a mathematical way. So we load B. So in the registered NB, we have loaded B. We have loaded here B. We apply QP. And if you remember, QP has the control of the QP is in these qubits. That's why you can see the eigenvalues are stored in the L register. So lambda j, the eigenvalues, this is a NL bit eigenvalue representation of lambda j. Next, what we have is a control rotation where the rotations are controlled over this register. That is the first NA register. So once we rotate with the control on the ancilla qubits, the eigenvalues are inverted. You can see on the registered one, we have lambda inverse already here. So to get the values of lambda inverse, we need to measure it in the basis of 1. We need to measure 1, and the accompanying coefficient of 1 contains our lambda inverse values. So when we do a QP inverse, so what QP inverse essentially did is, if okay, I'll just switch on the. So you see that NL had lambda j in it. The lambdas were stored in the NL register, and now after QP inverse, the NL register is again 0, and we get back to the original way, and it is now the A inverse is now present there. So what happened essentially here is, remember we loaded lambda j in the NL register. We now want to go to 1 by lambda j so that we can get the inverse eigenvalues. The control rotation helped us to do that. We went from lambda to 1 by lambda, and the 1 by lambda value got pushed onto the ancilla register using the same concept as in QP, the phase kickback. And then the QP inverse, it again brought back the lambda, it emptied the lambda, and again it is initialized to 0. Finally, when we measure the ancillary resistor, as we see here, the one outcome has the coefficient lambda j in it. So we need to repeat until the ancillars are all measured in 1. We discard the ket 0 outcomes, and then what we get is essentially, after measurement without any function on x, what we get essentially is this. So P1 here, P1 is the success probability of finding 1 when we measure it, because when we measure it classically, we can get either 1 or 0 with different probabilities. This is the expression of probability. We get the norm, and this is the final x that we have. So as you can see, this is exactly equivalent to what we are trying to solve, A inverse B. But not exactly, you can write it approximate because we have a non-factor here. This Bj, this factor, we have as a non-factor. So Uj on the B register is the B vector. Lambda J inverse is equivalent to the eigenvalues of A inverse. And we have our X vector stored inside this register. So we have X stored here. We have a solution X here. But now, since X is a quantum state, we have to find something observable, and so that we can kind of use it for a practical purpose. So that's the example that I will show and end today's lecture. So what we had done about 2 years ago, we were one of the first to apply this quantum linear solver algorithm to a quantum chemistry problem. Is we found, as I had mentioned yesterday, that to get to the exact ground state energy, one needs to improve upon the Hartree-Fock state. And to improve upon the Hartree-Fock state, we need something called electron correlation. So we need a measure of the instantaneous electron-electron repulsion. So there's a theory called the couple cluster theory. And the linearized version of it is called the LCC theory. And its equation can be very easily cast as in the form of ax plus b equal to 0. So this is exactly the kind of equation we need for using a HHL algorithm. So we thought that why don't we join these two concepts together and try to find the correlation energy at the LCC level of theory using a quantum linear solver algorithm. So the correlation energy expression for the correlation energy is given by this. So minus b dagger. So the complex conjugate of the vector b multiplied with A inverse b. So basically this becomes an overlap between the vectors b and our solution vector, which we are finding by HHL. If we can find a way to calculate the overlap of the solution vector of HHL with our starting input vector of B, then we can get this scalar value by measuring the classical registers. And this we can compare with classical computation benchmarks. So we can benchmark it with classical data benchmark. So this is what we did, and we got very good results. I'm not showing the results here. I will just show the algorithm by which uh, the overlap between two vectors can be taken by a quantum circuit. So it's very easy to do in classical mathematics, but using quantum algorithm, there are very few ways to get overlap between two vectors or two quantum states. I will just show one of the methods, which is called a controlled swap test method. Okay, so sorry. Okay, as I mentioned that I'll show the example of finding the overlap between two separate quantum states using an algorithm called the controlled swap test. It measures the inner product of any two vectors, and how it does it is, so what is a controlled swap? Have you studied about the swap gate in quantum computing? Uh, I also mentioned it a bit earlier also in my lecture. It just swaps the two qubits. And control swap is just, this is the swap gate. This is the swap gate. And the control swap is just a 3-qubit gate, which is controlled on this. So if this is 0, then it doesn't swap it. If it is 1, then it applies a swap. So say we have phi psi, we apply control swap. If it is 1, if this is 1, then the state becomes psi phi. So there's a swapping of, as you can see, the states are swapped. From phi psi, it becomes psi phi. So this is the basic work of control swap, and control swap can be used to find the overlap between two states. So the example that I will be showing is between two arbitrary states, phi and psi. You want to find the overlap. So what is the overlap? It's basically what we want to find the value phi psi or psi phi. It is equivalent. We want to find this value using a quantum circuit. So this is the quantum circuit that does it. We have a Hadamard, a control swap, another Hadamard, and we measure, we get the psi, we get the overlap. So how does it work? So this is the simplest method to get the inner product of any two states. Simplest quantum circuit. So as I was saying, the matrix forms of swap is this. So the matrix form of a controlled swap will be just this is the swap. This is identity. So as you know, as you already probably know, that from the quantum computing or quantum circuit lectures, that any controlled unitary matrix is equivalent to identity 0, 0, and the unitary. So that's how we get the matrix. So the control swap is a 3-qubit gate, and the dimension. So since it's a 3-qubit gate, the dimension of the matrix will be 2 to the power 3 cross 2 to the power 3. So it's an 8 cross 8 matrix. 3-qubit. So the matrix dimension is 2 to the power 3 cross 2 to the power 3. So it's 8 cross 8 matrix. So moving on how this actually Hadamard, then a control swap, and then another Hadamard. This actually finds the overlap between two vectors. Okay, so if you remember the circuit, it was like we have a Hadamard first. So let me just quickly draw the circuit, or else I have to move between slides again. So the circuit was like we have 0, we had psi, we had phi. There was a Hadamard here. No, sorry. I think it was the reverse. The Hadamard, yeah, the Hadamard was on the 0, right? Yeah. So we had the Hadamard, the control swap, another Hadamard here, and then we measure. So, oh, sorry. So we have first the Hadamard is acting on the 0 phi psi phi case. So the action of Hadamard on 0 is 1 by root 2 0 plus 1, as you know. So it's a plus state. Or plus state. Phi psi remains unchanged because there is no gate acting on psi and phi. Next, we have a control swap. The control is over this qubit. This one, since this is on a Hadamard basis, so we have both 0 and 1. So when it is 0, nothing happens. The swap doesn't affect the state psi and phi. When it is 1, they're interchanged. So when it is 0, it stays the same. Here it is exchanged, swap. So we have 1 by root 2 psi phi psi 0 plus psi phi 1. We apply the Hadamard again. So what this does is it further superposes the state, and we get the 1 by root 2 goes to half because another 1 by root 2 is multiplied to it. So basically what happens is this becomes, when Hadamard acts on 0, it becomes 0 plus 1 by root 2. When Hadamard acts on 1, it becomes 0 minus 1 divided by root 2. Root 2 into root 2, it becomes half. So we have phi psi 0, phi psi 1, psi phi 0 minus phi phi 1. And if we kind of collate the just normal factorization, we get phi psi plus psi phi, phi psi minus psi phi. Since the ordering here doesn't matter, we finally get so when we measure after transforming it into the Hadamard basis, it becomes square. So what we had was we squared these two, phi psi plus psi phi square, phi psi minus psi phi square. And what we have finally is 1 plus phi psi square. When we measure 0, we have 1 plus phi psi square. So basically, what we did, just let me just recap. At the 0 register, when we measured the final ancilla register, that is this one. When we measure here, when we get 0, we can get either 0 or 1. So the probability of 0 will be equivalent to this one. And since it's a probability, it would be just a square. So phi psi psi phi square plus so this and this are the same thing. These are equal. So are these. These are the same quantity. So we get twice into phi psi square plus psi phi square. So it's a complex conjugate of each other. Phi psi phi psi. If you take a complex conjugate of it, it basically becomes this one. So psi phi. So these two entities are complex conjugates of each other. So when we add them, we get the mod square of it. So finally, the overlap of the two vectors are basically what we get from the probability of getting 0. The value that we get, the number of times we get 0 when we measure the ancilla qubit. If we multiply 2 with it and divide by 1 and we square root it, we get the overlap value between the two. So this is how it is done. And so basically, if we kind of translate it back to what our problem statement was to find out the correlation energy, which is given by minus Vx. So if you remember, we did HHL. The output from HHL was X. So with the HHL circuit that we had, so to apply HHL to the chemistry problem, what we have to just do here, we had in this register, we had X. We take another register here. Say I'm calling it M. I load the vector B here again. So from this line, we have X. From here, we have B loaded. We apply the swap. So say I'm calling it Hadamard XX Hadamard. And from this, for getting the correlation energy, we will need another additional set of register. So the number of registered here is large. And also you can see, as I had said, the QP itself is a very deep circuit. So we have QP here twice. So both of these are deep. We have a control rotation that is not that, costly. But we have 4 resistors here to get the correlation energy. We also have twice QP twice. So this is a rather very long circuit also, and it will be useful when we get like better quantum computers in the future. So, so that is it for today's presentation. Basically, I tried to present 2 fault-tolerant algorithms and their direct equivalence as an application to quantum chemistry. Tomorrow, Professor Guidoni will present like NISQ algorithms, which are directly now applicable, like the variational quantum, like Professor Daniel Arbon was also talking about. So if you have any questions, please. Yeah. If we slightly more circuit.
If the molecules are
Small. Or if,
small,
okay.
when is it
When the molecules are small or large, what are you saying?
large?
Yeah, yeah. Then also this will be, the precision will be high with better quantum computers, even when the system size is big.
When they say that
Hmm.
there's a lot of mess.
Lot of noise. That's why we're waiting. I mean, these are called the fault tolerant algorithms because it depends on that. If there are a lot of noise, we will have a lot of qubits so that they can correct the noise. So what usually the quantum computers that we're waiting for, they will have so many qubits in them that only a small part will act as what we are writing here, what we are always drawing here. Like these are only a small part. There will be more qubits above it, which will be there just to correct the noise from the system. So that is what we're waiting, basically.
So when you say advanced levels of use last what you said, when is the
Yeah.
advanced?
When we have more qubits in the quantum hardware, more number of qubits. Yeah, I'm done.
You try,
No, it's not.
you want to see the,
No, I want to stop the sharing.
here,
Okay.
in the.